some more calculus derivative application problems. We're now looking at word problems. Okay, all this is applying our maximums and minimums to a real world type situation. Okay, the hardest part here is going to be your setup, and then other than that, we're taking the derivative, finding our critical points, finding those maximums and minimums. Okay, so got an example here. We have a farmer with 4,000 meters of fencing, and he wants to enclose a rectangular field alongside a river. If the farmer does not fence the side along the river, what is the maximum area? So just like we did with related rates, we could go ahead and find what's given, what is being asked, and get ourselves a sketch. That's going to help us set up this problem. So given here, we know that we have the 4,000 meters of fencing and the area. We're given that we're going to be dealing with a rectangle, and one side of our rectangle is going to be a river with no fence. So I'm going to go ahead and just kind of get a sketch of that. So let's just say here's my river and here's my fence. More rectangular, but you get the gist. So I'm going to go ahead and call these two sides X, this side Y. That is the fencing that I'm going to be using, and my fencing is my perimeter, the 4,000 meters of fence. Since we're looking to find the maximum area, that's what they're asking for, I'm also going to find the area of my rectangle, which is just X times Y. So what I've set up here is a system of equations. I could take the derivative of area here, but I'm dealing with these multiple variables, X and Y. So I'm going to actually use my perimeter formula so I can make a substitution before I take the derivative. So I'm going to go ahead and just isolate Y. So here I'm going to see that Y equals 4,000 minus 2X. So now I can substitute this Y. So my area equals X times 4,000 minus 2X. So here's my area formula, and it's in terms of one variable, so that's going to make the derivative easier to deal with and finding those critical points. So again, to make my derivative a little bit nicer, I'm going to go ahead and distribute here. So area equals 4,000x minus 2x squared. Again, I've done some work here, but I don't want to get confused. This is the area formula. It's not the derivative. So what I'm going to do now is I'm going to take the derivative so I can find my critical points, so I can find maximums and minimums. So when I take the derivative here, a prime equals 4,000 minus 4x. And when we find our critical points, we go ahead and set our derivative equal to 0. Like such. So isolating x here, I'm going to get my critical point, x equals 1,000. So if I were to test that, if you remember testing our critical points on the first derivative test, if I assign x less than 1,000, let's say it's 1. 4,000 minus 4, well, that's a positive value. Okay? And then if I pick a number larger than 1,000, let's say 2,000. 2,000 times 4 is 8,000. 4,000 minus 8,000, that's a negative number. So here I'm seeing I'm increasing until x equals 1,000, and then I start to lose area. So when x equals 1,000, that's going to be my maximum area. Okay? So if x is 1,000, I can plug that in here. 4,000 minus 2,000 times 1,000. Y equals 2,000. So the question is asking, what is the maximum area? Maximum area happens when x is 1,000 and y is 2,000. So that is going to give me an area of 2 million meters squared. Okay? So again, starting with the given, what's being asked, get yourself a sketch, and then build your formula from there. So that's the first example. Just for time's sake, I'm going to go ahead and turn this into a second video just so you have two options. You don't have to watch 10. Do I care? I do care. But if you want to watch the second example, you could just jump to this point in the video. I'm just going to keep filming. Okay, here we go. Second example. So we have a sheet of metal that is 18 centimeters by 18 centimeters because it's square. We're going to remove a small square from the corners, and we're going to turn up the edges to create an open box. What are the dimensions of the box with the largest volume? So we have a piece of sheet metal, looks like this, and we're going to cut out corners, and we're going to fold them up and create the open top box, like this. Okay, so we know that this is 18 by 18, and we're going to cut out these little pieces. The little piece, that's going to change. We don't know what that equals, so I'm going to assign that to be x. And again, these are squares, so the measurement's the same. We want to maximize the volume. So the volume of a box is length times width times height. So based off of this, my length here is going to come from this measurement right there. Once that's cut, we're going to fold it up, and that's going to be 18 minus 2x. My width here is also going to be 18 minus 2x, and then the height is going to be...
Catherine Judge, please come to the main office or contact the main office. Catherine Judge, thank you.
The height is going to be x. So here we have our length times width times height. We're creating our volume formula for this box. Just like this. There's our volume. And all we got to do is maximize that. To maximize it, we're going to take the derivative, set it equal to 0, and solve. To do that, I'm actually going to FOIL this together to make my life a little bit easier. And I'm going to quick use a calculator to do some of that for me. So 18 times 18. This is going to be 324x. 18 times 2 times 2. That's going to be negative 72x squared plus 4x cubed. So some quick foiling there, distribution. Here's my volume formula. I'm now ready to take the derivative. So I'm going to take the derivative of my volume, which is going to give me, I'm going to switch the order while I do this. I'm going to do 12x squared minus 144x plus 324. Now that I've got the derivative, I'm going to set it equal to 0, and I'm going to solve by factoring. So I'm going to go ahead and factor out the 12 to make the factoring easier. And I see that my two factors are x minus 9 and x minus 3. So that tells me my critical points are 9 and 3. So if we take that into account really quick, we could easily, we could think about it logically, or we could put it on a number line here. If my corner that I cut out here is 9, and my full length is 18, cutting 9 out, that's actually the end of our domain. That's as far as we could cut, so we can't even go past that. And we could say the start of our domain is 0, because if we don't make a cut, we have 0 volume. So here's our intervals. Let's say we plug 1 into my derivative. I'm going to get a negative, negative, so that's going to be an increase. We're going to see an increase in volume until we hit 3. And then if I plug in 4, negative times a positive, that's negative. If we make a cut larger than 3, we're going to start to see a decline in our volume. So our x equals 3, that cut is going to create the largest volume. So we're looking for the dimensions of our volume here. So 18 minus 6, that's going to be a 12 by 12 by 3. Okay, and these are centimeters. The dimensions of my box. And I believe our volume is going to be the 324, right? Nope. A little dyslexic on that one. 432 centimeters cubed would be our max volume. Okay, long video, 10 minutes, 2 great examples. Make sure you set up your equation, then take the derivative, find the critical points.